Hello everyone. Welcome to today's live session. I'm Divya and I will be walking you through a practical data-driven analysis of Ladle refining furnace process. Okay. So this is the agenda of our today's session. And so here we are going to discuss business. We will start with business understanding and the challenges faced, then look at our data flow architecture, and followed by how we collected the data. And we did exploratory data analysis and pre-processing. Finally, the insights drawn from the visualization. Okay, so let's start with the core business problem. In steel manufacturing, the ladle refined furnace plays a key role in determining alloy quality. So we aim to optimize the sampling and reduction process using historical data to reduce waste and improve yield. Okay, so here I highlight sampling frequencies and then improve process control, and then we have to minimize energy and material waste, and then business objective. So the business objective is a goal. Okay, so the goal is to create a system that make a data-driven decision to minimize the cost and improve the quality. But as with any industrial setup, we have a business constraint, such as the need for a real-time processing, and then regularity compliance and cost-effective scalability. So, and what about the success criteria? So here we have business and economic success criteria. So increased yield, so more high quality ferroalloy needed, and then reduced downtime, better operational flow, and then lower cost, material and energy efficiency. So this is the project architecture. So this is a visual representation of how data flow through our project. So it includes raw data collection from the furnace log, and then pre-processing and exploratory data analysis, and then eventually actionable insight. So here is a research article. So here you can see the data set over 2,600 rows and 35 columns. So it records the elemental composition before and after LRF treatment, and it includes the targeted composition. Okay, so this provides a rich source and analyze the element behavior. So here, before diving into analytics, it is important to understand what each column in the data set represent, such as carbon, and then manganese, and sulfur, and phosphorus for both pre and post LRF treatment. Here you can see statistical insight. So in the exploratory data analysis stage, we look at like central tendency. Central tendency means mean, median, and then skewness. So most elements are positively skewed. Sulfur and phosphorus are negatively skewed. And then kurtosis. Carbon, silicon, manganese have a high peakness. And then outlier are present, especially in the carbon and manganese. Here you can see statistical insight and business insight. So here, in mostly all elements are positively skewed. Okay. Here, sulfur and chromium optimize high sulfur level, and sporadic chromium spikes indicate area of the better control. Okay. So next, data pre-processing. So after EDA, we clean and transform the data. So typecasting, handling duplicate, and then outlier treatment, zero and near zero variance. So after performing EDA, we go for data pre-processing to transform unorganized data into organized data. What is typecasting? It is used to convert data types. For example, date column change from object to date time. Duplicate. What is duplicate? It will check whether any duplicate value is there. So no duplicate found. And then outlier treatment. So it is treated using IQR method and capping. Zero and near zero variance, none found. So missing values. So this is also continuity of data pre-processing. So missing values, none. Checked if there are any missing values. And transformation. So here we applied Yo-Johnson method to handle both positive and negative skewness. Scaling, data scaling. So here used robust scaler to handle extreme value. And then discretization. So discretization, it convert numerical value to categorical bucket for simplified visual understanding. Then we move to visualization part. So here you can see data visualization. Okay. So here total heat count 2655. So this indicate here, so all over the dashboard, metal used and then grade and then chemistry. So here it indicate the number of furnace operation analyzed. So least used metal, final boron, 0.79%. So it suggests boron is rarely needed or added. So most used metal is what? Final manganese. Okay, so manganese is the most critical alloying element in this grade. So here you can see bar chart and then average distribution of open chemistry by grade. So this compares average elemental composition for a grade 800, 801 and 802. For example, grade 801, it shows a higher aluminum and titanium content. So it is useful to understand variability across the grade. And then another bar chart. So it is aimed to usage of metal composition. Okay, it represents the target level for element like C and AIM, silicon. Okay, so grade 802, it consistently has the highest target for manganese and phosphorus. So this help benchmark actual and versus aimed performance. And then pie chart. So pie chart, maximum usage of manganese by grade. So grade 802 contribute 38% of magnesium usage, and then grade 800 and 801 have approximately 31% of ease. So it indicate manganese demand is heavier in higher grade steel. Okay, you can see the column chart. So here metal composition before versus after LRF. So this comparison shows manganese is the highest rise post refining. So silicon and phosphorus are relatively stable. So this validate the efficiency of the refining process in the element balancing. So next, here you can see. So top card, here also count of heat and then line chart. So this line chart, the final composition trends over the month. So it track month-wise trend in the metal like aluminum, silicon, manganese. So manganese is consistently high, useful for understanding process stability over a time. And then you can see tree map. So the tree map average composition before LRF. So manganese dominate, followed by carbon and silicon. So easy visualization of element proportions. And what about the donut chart? So average, like total F magnesium by grade. So it reiterate magnesium usage, a grade 802 again leads. So pie chart helps quickly segment grade-wise usage pattern. Okay, so it confirms like actual versus target. So in some case like aluminum and then carbon, a final value fall short over the shoe target. So the powerful quality control check you can see. Okay. So here also aimed composition by grade. It shows the different target composition 800, 801, 802. So grade 802 has the higher target. And this aligned with the demand of toughness and hardenability in a higher grade. And then initial and final composition bar chart. So it displays how much composition changed during the LRF process. So manganese and carbon shows significant shift reflecting alloying and refining. So the maximum composition of metal at initial stage, higher record value, magnesium, and then carbon and indicate extreme values existing in the initial stage. Hex map. So heat count by the grade over a date. Okay, so you visually cluster furnace operate across dates and grades. It helps to identify high activity days. So manganese distribution heat map, it reveals the grade-wise manganese dispersion. So a red zone shows how heavier usage. It's final one. So grade 800, grade 800, grade 801, grade 802, 8, high in carbon and manganese, more chromium, and then higher aluminium. So final composition trends by the grade. It tracks how final metal content evolves across grade 802 and 800. Some metals like magnesium, carbon show a consistent increase with grade complexity. The table. So this is relationship between the metal. So grade 802 shows 115 and then 28, magnesium 326, carbon. So it helps understand independency and which metal pairs are correlated in composition. And then you can see the bar chart. So this is distribution of aimed composition. So it break down the target element level and each grade. So grade 802 again reflect high PAIM and then CAIM, suitable for high performance steel. Final insights. So manganese is the most significant metal in both composition and variance. Boron. So boron is consistently the least used, but it's still crucial for specific steel property. Then grade 802 demand highest refinement and consistency. So this visualization support decision in process control and sampling frequency, alloy cost optimization. Okay, in stakeholder point of view, so what is the main benefit of the analysis of this production? So this analysis help to identify which alloy are heavily used, right? Which alloys are heavily used and use how actual usage compare with aimed composition. So this allow the plant to optimize alloy addition and reduction wastage and maintain consistency in grade quality. So if you ask me, can this help reduce operational cost? Yes. Yes. By identifying overuse or unnecessary addition of element like magnesium, carbon, we can lower the material cost further. So this trend analysis help to predict composition accurately. So according, you can avoid costly rebolds or quality rejection. So how does this dashboard help us to maintain grade quality? Yes. So this dashboard compared aimed and final composition for each grade 800, 801 and then 802. So it like flags deviation for the key element like a carbon, silicon and sulfur. So it is enable proactive control before sampling go out of the spec. So here, which element show the most deviation from the target? Manganese. So the manganese consistently shows the highest variation in the final value, especially in the grade 802. So this insights prompt tighter process control or better forecasting for manganese absorption. If you ask me, what operational pattern have we uncovered? So heat frequency and grade-wise manganese usage over a time shows that the grade 802 operation are more manganese intensive. So also the heat map reveals batch days with high element deviation. So it is helping you to schedule corrective maintenance and calibrations. And one more question. Can we predict alloy usage for further heat? Can we predict? Yes. With enough data, a regression model, it could be built using historical trend to predict alloy demand per grade per day. Okay, what data pre-processing and modeling step we were taken? Outlier using IQR, transformation via Yo-Johnson's to normalize skewed data, and then feature scaling using robust scalar, and then correlation mapping for feature reduction, and then grade-wise grouping for comparative visualizations. If you ask me, would this data feed a real-time prediction model? Yes. So the cleaned data set and real-time sampling log can train a supervised model to predict the post-LRF composition. So flag anomaly risk and it suggests alloy corrections. Okay. So what is the most underrated metal across grades? Boron. Okay. So boron 0.79% is the least used metal. So it indicates it's only used in specialty steel application or added sparingly. So, and why grade 802 showing a consistently higher value? So the grade 802 is likely high strength or high hardness steel. So it demands high concentration of manganese, phosphorus and carbon, which is why it top and short in the composition. Thank you.